Thank you and welcome to the channel on the ozone technology course. This session is session 11B and I'll be discussing the concept of the corona discharge for the production of ozone, the application and the issues in generation as well as limitations and the advantages. The corona is defined as a pale blue light generated when air flows at a very high voltage between two electrodes. Now this voltage can be applied as high as 25,000 volts. This mimics the lightning and similar to that which causes formation of the ozone during the thunderstorms. Please note there is a big difference between a corona and a spark. A corona generates special energy, a spark generates heat. As explained in the nitrogen cycle, nitrogen is also oxidized at a very high voltage to form nitrous and nitric oxides. These reactions are activated by moisture, which acts as a catalyst. The moisture also dissolves the acid gases to form the corrosive acids. This is a very serious problem with the corona discharge method. The diagram on the right shows a typical ozone generation cell using the corona discharge. You will notice that there are two electrodes. One is a ground and the other one is a high voltage. There is a dielectric between the electrodes, which is not a complete conductive material. This dielectric is generally silica glass or ceramic. When high power, high voltage is applied on one end using the transformer and either air or oxygen is passed through between the two electrodes, the oxygen dissociates as it proceeds along the cell tube and forms ozone. It's quite obvious you wouldn't expect a complete conversion of oxygen to ozone, but it will be a concentration of ozone in a mixture of oxygen. If air is used, then it will be an ozone-air mixture. The formation of ozone from oxygen or from air is an exothermic reaction. This means when during the conversion from oxygen to ozone or oxygen from the air to ozone, heat is generated, and if it is not cooled, there might be a overheating, and heat also reverses the reaction of ozone and which converts to oxygen so that the output can be drastically reduced. Therefore, there must be an adequate cooling of the cell. We can use either air to cool or with a more effective cooling with water circulation. There are two methods of producing the corona discharge cell. The first method, which was an older method, some 50 years ago, or 50 to 30 years ago, they used to have a glass tube or silica tube through which there is that electrodes and through which the air or oxygen passes through and ozone is generated. The corona is discharge takes place between the two electrodes and in the glass or silica tube. There are some issues with respect to the production of ozone. Firstly, as I did explain, it is exothermic, heat is generated. And secondly, if a different voltages are applied or the conductivity is too high, then instead of corona you get a spark. And spark means its heat generates and it will start making pitted holes on the glass and destroy the cell. There is a limit on the length of the ozone cell, which I'll be discussing later. There's a limit on the quality of the feed gas, which is also going to be discussed later. Now, the newer methods, they are using plates, either glass or silica, and electrodes, positive electrodes, which is interfaced. So air passes through the gaps between the plates as shown in the diagram, or oxygen can pass through, and you have output of ozone. As usual, there's a limitation on the length of the cell, but in the plate method we can create so many plates in such a small space that we are able to produce a very high output of ozone. This slide discusses some of the issues that are present when we use the corona discharge system. Firstly, the frequency and the voltage are critical so that we generate a corona or plasma instead of sparks. A corona or plasma is a pale bluish color and there is no sound when the corona is discharged. If the voltage is higher or there is an issue with the conductivity, then sparks will be discharged and there will be noise. The quality of glass of the cell is critical. It must be quartz. Normal soda glass, first of all, is unable to withstand the high voltage stress and is not suitable for use as a cell of ozone. But whichever glass is used, if there is corona formed at any time, the corona will start pitting the glass insides of the glass cell and the output of ozone is compromised. All materials that we use when we make the ozone cell, including the ozone O-rings, etc., must be ozone resistant. The feed gas flow rate must also be optimum. If you pass too much of feed gas, there will be ozone product produced, but it will be diluted. If you pass too little feed gas, you will have a good output of ozone, but also at lower volume and therefore less concentration or less output. Other issues like dust, moisture, etc. may be collecting on the surrounds of the cell. Dust is a real poison for the cell because the dust conducts electricity and it might causes shocks and sparks. The pumps and tubes used in the passing of the ozone gas or ozone air mixture must also be ozone resistant. Nylon, for example, cannot be used. It deteriorates into powder. Rubber cannot be used as ozone attacks rubber. The quality and quantity of ozone produced depends upon the following. As I said, the quality of the feed gas. If the feed gas is air, then the air must be dry with a dew point below minus 45 degrees centigrade. This is to ensure the gas has very little moisture. Moisture acts as a catalyst to form secondary reactions between ozone and nitrogen, competing with the ozone formation. This can be done by using compressed air, not less than 50 psi, removing compressed air, not less than 250 psi, removing the moisture with filters. Nitrogen reacting with oxygen in the cell results in ozone dissolving the moisture to form acids and will cause corrosion down the line. The alternative is to use oxygen generated by passing compressed air to a nitrogen separator. Formation of ozone from oxygen has no issues with nitrogen acid formation. The quantity and quality of ozone generation with the corona discharge systems depends on several factors. The frequency and the voltage applied, the distance between the electrodes, the nature of the electrodes, the number of cells, the quality of feed gas, air, dry air or oxygen, the quality of materials used in the manufacturing of the cell, the temperature at which the ozone is generated. This picture shows a typical commercial ozone generator. The tube, this is the tube methods. You find that an electrode is within the center of the tube, and the outside of the glass tube or silica tube becomes the negative while the center becomes positive. Then you have an outside cooling jacket which cools the heat produced during the ozone production. The cooling water goes onto one end and comes out from the other end. The high voltage is applied, goes straight to the electrodes. The air is pushed into one, air or oxygen is pushed into one side, and the oxygen and ozone or air and ozone is delivered from the other side of the equipment. You can have maximum number of glass tubes so as to increase the output. So the more glass tubes you have, the more the cells and more output of ozone. So the equipment can be a very huge equipment if it is to be produced kilograms of ozone per hour. Thank you very much for having the patience to listen to this session. This is the end of this session 11B. Please go to the next session 11C for the principle of ozone generation using electrolysis of water. If this is your first tune-in, please visit sessions 1 and 2, which gives the complete program details, and sessions 3 to 11B, which is the course in the ozone technology. Please click the like icon or the subscribe icon, which is very important, so that I'll be able to notify you of the uploading of the next session. Thank you very much and have a very good day.